Okay, so I'll repeat my comment. Uh, in my mind, all the solutions they find raise 10 to the power of something questions for every solution. So yeah, more questions than answers, as always with these things. Where does one start? I mean, if they say mass, I remember watching one video where they were explaining a bit more about the Higgs, how the Higgs gives mass. But in that video, the guy was saying the Higgs only contributes a small amount towards the total mass. Most of the mass is derived from the energy of the quarks inside protons and so on. You know, Einstein's old thing of energy being equivalent to mass. So when they say at the beginning of the universe there was such high energy that there was no mass, to me that's a contradiction to the other statement where energy is equivalent to mass. So it's something which, you know, statements are made which raise questions in my mind to which there seem to be no answers. I see Laura out. Anybody got some comments and questions and answers?
Yeah. Derek, just from me, first of all, that was absolutely fantastic. Thank you so very much for doing that, or giving us the opportunity to watch it. I recently listened to three researchers discussing their current field of interest, and that was about the electron. And they were saying that it is strange that the electron with a unit charge of 1 and the quarks each having partial charges. And that's their field of research. And they were saying it's so odd that they eventually found one another. They obviously offered no answers, but just that's what they're researching.
Well, to me, it's a bit like, not like various different things wandering around and finding each other in the universe. To me, they're more like parts, opposite parts almost of the same coin. They were, the fact that they are separate entities doesn't mean that they were wandering around in their own sort of thing and then finding each other and making an atom. I don't know, maybe that is right, but to me that's not, doesn't make sense.
At what time did the Higgs field appear? It sounded like you said a quadrillionth of a second. Did I hear correctly?
Sorry, what? Sorry, a quadrillionth of a second. I was saying about what?
At what time did the Higgs field appear to give mass to the various particles?
That sounds familiar, but I'd have to go back and see what he said at that point. What is your, as far as you know, what is the right thing there?
Well, I think a cutoff is inflation. And that, if I remember correctly, happened between 10 to the minus 36 and 10 to the minus 34 seconds after the Big Bang. And in my mind, when inflation happened, the fundamental particles that you were describing now, the particle zoo, had mass. Do you agree with that interpretation?
Yeah, if you look at the research, all the things where they got all the information from, in if you on the YouTube video at the bottom, you know, where they list everything, they seem to have done quite a thorough job of getting all the correct information together. But I wouldn't be surprised if there was some slip of the tongue somewhere. So maybe it's a good thing to follow up and just check on. I'm quite interested actually.
But it must have been very shortly.
Yeah.
After
the Big Bang. Quadrillionth, what did you say? 1 to the 10 to the minus 36 or something? That's very, very much smaller than a quadrillionth.
What is a quadrillion?
Well, I don't know. What is I suppose you have a billionth. You have a millionth, then a billionth, then maybe a trillionth, and then maybe a quadrillionth is 1,000 times smaller than a trillionth. So what is a trillionth? Is 10 to the minus 12. So I should imagine a quadrillion is 10 to the minus 15. So 10 to the minus 36 is much smaller. Does that make sense?
Quadrillion in numbers is 3, 6, 9, 12, 15. Yes.
15. Yeah.
10 to the 15th.
Yeah.
How many billions in a quadrillion? Well, that's
A million. There are a million billions in a quadrillion. Because there's 1,000 billions in a trillion, and there are 1,000 trillions in a quadrillion.
Yeah, well then he must have used another term, a term other than quadrillion for the second, because it was way before then, much shorter.
Yeah. All right. I'll give it another listen and see if we made a mistake.
Oh, I don't think
If I
it's
made a mistake,
important.
I'll put it in a comment and I'll say, Dr. Pierre de Villiers says you made a mistake.
No, that's not true. Your comment about energy, or the mass associated with energy outweighs the physical mass, I think is correct. But it's still totally overwhelmed by the fact that this whole standard model of particle physics describes 5% of the mass energy of the universe, or less than 5%. And we have no idea where the other 95+% comes from or what they might be. Lots of speculation, lots of theories and proposals, but we still don't know.
Okay, but that's if you accept the standard theory. And I'd like to show 2 5-minute videos by Sabine Ossenfelder, which seems quite convinced that both the recent so-called theory about dark energy being caused by black holes, and also the other one about the findings of the James Webb Telescope finding galaxies which are far too complex and far too big at the early stages of the universe than they should exist. Well, let's see what she says, but I did tell Peter what she was saying in that video, and I thought it was very interesting. I'd like to look at this now when we finish with the discussion.
I've looked at both of them, and Ossenfelder is a usual controversial self, and I think the James Webb conclusion is not quite a conclusion. It's one interpretation.
Yeah, but I think what she said is very interesting. And because it's controversial, probably it's why I find it interesting. All right. So, yeah, I think that was quite well put together. I'll make a note to check on the what is it when the Higgs boson came to existence? At what time after the Big Bang? I'll just go back and find what they said and when they said it.
No, Derek, I'll Google it and find out.
Okay, but I'd just like to see what they said and whether they actually made a mistake, because
no, I don't think
there have been times in some of the other videos where I thought what they said wasn't correct. About various things. Sometimes, people that narrate things, maybe they make mistakes sometimes. So it's important that we make sure of our facts. When we talk to people, we don't repeat the incorrect information. All right. Are there any other comments, or can I play those two Ossenfelder videos quickly? Let's see. Webb finds galaxies that shouldn't exist. So I'm just going to share this quickly. Where's my Zoom gone to? Share screen. Right. So this is, I'm just starting it here because this is where she starts talking about it.
Probably seen the headlines. The James Webb Space Telescope seems to have discovered 6 galaxies that shouldn't exist. The news isn't all that new. The data came out last summer and the analysis appeared on the preprint server. It's just that now it's been published in Nature, so it's kind of official, I guess. The conundrum is that these galaxies are big, but they existed already when the universe was only between 500 million and 700 million years old. According to the standard theory of cosmology, that's the one with pass C, call a curious case of baby galaxy gigantism. You can see it in this image. The red blobs appear to be 6 massive, densely packed galaxies. The mass of their stars is at least 1 billion times more than the mass of our sun, and in one case about 100 billion times more. The images were taken with the Webb's near-infrared camera and then cross-checked with images from the Hubble Space Telescope, which had previously looked at the same locations on the sky. You probably read all this in the popular science news. What you might not have read is that these big early galaxies were a prediction of modified Newtonian dynamics, also known as MOND. I talked about this prediction in a video a year ago. What these observations do is that they falsify dark matter and support MOND. And it isn't the first observation which has done that. It's happened several times before that MOND made correct predictions when dark matter didn't. I think science writers should pay a little more attention to this. What do you think, Albert? In February last year, the European Centre for Disease Prevention and Control
Okay. So that was that one. Any comments on what she said there? Yeah.
No. I think if those observations are correct, we do, well, astrophysicists will have to rethink the evolution of the universe. There's no doubt about that. I'm not sure that MOND is the way to do it. It's a theory that does, it also makes a few other predictions which are better than dark matter. But as always, she's very sure of herself, and she's got the backing of Einstein.
Yeah, Einstein nodded. So, yeah. Well, I think it's interesting times. I think the James Webb, I think it's fantastic that we are living through what we find with the James Webb. All right. Then can we just look at the other one quickly while we're on about the dark energy one?
Just one comment, Derek.
Huh?
I remember in a number of talks I've used the term that the Hubble Space Telescope has been the single scientific instrument that has contributed more to an understanding of the origin and evolution of the universe than any other instrument. And I honestly believe that. I suspect that the James Webb Telescope is going to supplant Hubble, if it hasn't already done so, as the biggest contributor to our understanding of the universe.
Yeah, I think it's fantastic. I tried to, by the way, I saw a video where somebody was downloading James Webb images and processing them the way they liked. So I thought, oh, let me try the one of where it did the sort of center of the tarantula, all that star forming region and so on. So I went to the MAST website, they call it, where all the data is from James Webb and Hubble and so on. And I wanted to download the images, but each image which you had to use to make a composite image was over 1 gigabyte big. And the download speed, I've got a fast download speed on my end, but at their end, they only seem to upload to you at about 2 or 3 megabits per second. And it would have taken like 20 days to download one image at that speed. So I just gave up. I don't know if there's a better way of doing it, but I'll look for it. Okay, can we go on to the next video? Last one quickly, let me go find it. I think it's this one. Dark energy, yeah. All right, can you share this one?
Welcome everyone to this week's Science News. Today we'll talk about whether dark energy is made of black holes, 4 types of solar systems, exoboots, whether banning short-haul flights makes sense, 3D printing with sound, smart contact lenses, how copper makes fuel, a new method to extract carbon dioxide from seawater, and of course, the telephone will ring. A lot of people have asked me to comment on a paper that made headlines last week by claiming that black holes are dark energy. So here we go. All stuff in the universe carries energy. Mass is a type of energy because E equals mc squared and all that. But the universe contains different types of energy. The best current data say that about 4% of the energy in the universe is normal stuff like what we are made of. 22% is dark matter, and the remaining 72% is dark energy. Dark energy and dark matter are 2 different things with different properties and different effects. Dark matter is the stuff that makes galaxies rotate faster. Dark energy is responsible for the expansion of the universe. Black holes, as commonly understood, are neither dark matter nor dark energy. They are formed from the collapse of stars and subsequent mergers or accretion. They are made of and behave like normal matter. The vast bulk of these 4% normal matter is gas, either in galaxies or in intergalactic space. Black holes make up at most a few percent of those 4%. This by itself already tells you that the idea that black holes are dark energy is, politely speaking, difficult to make sense of. It would require a small fraction of 4% to come out being 72%. And if you can make that happen, then maybe you could make your magic work on my ad revenue. Thank you. But let's look at what they did in the paper. It's actually 2 papers. In the one paper, they did an extended data analysis of a sample of black holes in galaxies at different distances from us. Roughly speaking, the farther away the galaxy, the younger it is. So this means that data collects galaxies of different ages, and that allows them to infer how fast the black holes in them grow. They find that supermassive black holes grow by about a factor of 7 to 20 in 9 billion years, which is faster than expected from models of mergers and accretion. In the other paper, they then suggest that really these black holes might be made of dark energy. If that was so, then their mass would grow with the cosmological expansion, so that could explain the observations. And indeed, they find that the observed growth fits with this idea extremely well. A cynic might say suspiciously well, but we don't want to be cynical, do we? Be that as it may, just because the mass of an object increases doesn't mean it's made of dark energy. The defining property of dark energy is that it has a negative pressure that's equal in magnitude to the energy density. They don't explain how black holes would give rise to this negative pressure. They just assume they do. Let me just say I'm not particularly convinced by this argument, if you can call just assuming your conclusion an argument. For one thing, the theory is sketchy, to say the least, and they can, of course, not actually track the growth of black holes because that takes billions of years. Instead, they look at the typical size of black holes in a certain type of galaxy of different ages. There are a lot of uncertainties in going from samples of galaxies at different ages to the growth of black holes. Most importantly, we don't ever observe all galaxies, and we don't observe all supermassive black holes in those galaxies. So they have to extrapolate from the observed sample to the total population, and the observations have errors. So it's difficult to infer the black hole masses. They discuss this all in their first paper and conclude that if they account for all those uncertainties, they still can't explain the growth of the black holes, though I'd have expected the error bars to be larger. In any case, they propose a few other tests of that idea that includes precision measurements of the cosmic microwave background at low angular momentum, strong lensing of gamma ray bursts, and a couple of other predictions that are conveniently difficult to check. The biggest problem with this idea is the claim that there is something in need of explaining in the first place. Einstein's theory of general relativity has two free parameters. One is the strength of gravity, also known as Newton's constant. The other is the cosmological constant. The cosmological constant is a constant of nature, and it determines the curvature of empty space. It explains all observations currently attributed to dark energy. It doesn't have to be made of something any more than Newton's constant has to. I really think physicists are screwing themselves over by calling this constant dark energy. If they'd called it more appropriately empty space curvature, no one would think there's anything mysterious about it. It seems likely to me that soon enough someone else will come up with a perfectly mundane explanation for the data, and you'll never hear of this idea again. Meanwhile, I'd like to propose that really the universe is made of 100% dark humor. Now here's some real space news.
All right, comments on that one? Quite a lot said there, actually, I thought.
Yeah, well, the terminology, if the different name for dark energy is very descriptive, and I think it's a very valid point. If it had been called something else, what she's essentially saying, or what I interpreted as saying, it doesn't have to be comprised of anything. So even asking the question, what is it comprised of, becomes irrelevant because it's the curvature energy of empty space.
Yeah. So, yeah, I think she says a lot. What she says, she tries to reason everything quite well. You know, she tries to base things on reason and strict scientific approach and so on. I think I always like her approach. You know, it's difficult to argue with what she says. I think sometimes she does hone in on a specific aspect and doesn't sort of bring all the other complications into her argument, but still, I always find her very interesting. All right. So dark energy. So what we have learned tonight, particles don't exist. Dark energy doesn't exist. Dark matter doesn't exist. Okay, nothing seems to exist, so why worry?
Well, fortunately, our perspectives of each other does exist, at least in our minds,
Yeah.
for which thank goodness.
All right. More and more
Thanks.
interesting as we go on.
That was interesting.
All right. Anybody else got more to say? Ask. Peter?
No, I just accept it.
Okay, David and Elaine. All right. I look forward to the day, one day, when somebody's going to come up with all the answers. But at the moment, we seem to have a universe full of questions and about 3 answers, which are cast in dark every second day.
That situation will remain forever, Derek. But however much what we know is the circumference of a circle, and what we know that we don't know is the enclosed surface, and that's going to remain like that forever.
Yeah, well, it keeps life interesting. Life would be very boring if we knew everything.
True.
All right.
Okay. Good night, everyone.
All right.
Thanks, everyone. Good night.
Thanks, Derek.